In the name of God, the compassionate, the merciful, engineering plasticity, chapter 3, yield criteria, part 7. So far, in this chapter, we have talked about yield focus, yield surface, and yield criterions like the Mises and Tresca yield criteria. In this part, I want to talk about normality and convexity. Normality and convexity are related to material stability, the Drucker postulate that we talked about earlier on. Now, we showed you that we have a yield surface, and this is, supposing this is yield surface. And we said that the inside the yield surface is the elastic region, so any point shown inside this surface is the elastic state of stress, and any point on the loci of the yield surface is the incipient yielding or start of the plastic deformation. And outside this surface is the state of plastic stress. Now, what we are interested here, I have talked about the yield surface and its shape. I said that the shape of the yield surface could be convex, it could be concave, or maybe a combination of both of them. So here we are going to prove that the shape of the yield surface must be convex, and the increment of plastic strain must be perpendicular to the yield surface. Okay, so the increment of plastic strain being perpendicular to the yield surface is the normality, and convexity means that the surface is convex. We are going to prove these two conditions. Okay, so as you can see here, we have a state of stress sigma star. Okay, it could be here or it could be there. Now, if you look at this, vector, it's sigma minus sigma star, and that's the state of stress on the plastic region or incipient yielding, and that is the incremental plastic strain. Okay, and this is the surface shown by F. Now, sigma star is where the state of elastic, okay, stress, elastic stress, and sigma is in the verge of plastic deformation or incipient yielding. Now, sigma minus sigma star is this vector, and in terms of the these vectors, in principal stress and plastic strain increment, this one, we have this equation for stability. This is the Drucker postulate, sigma minus sigma star dot d epsilon p. Okay, this is the Drucker postulate for hardening material. And so this must be positive. This dot product must be positive. Now, of course, dot products are positive if the cosine theta is positive. And what is cosine theta? If we continue this vector and put the beginning of this vector here, then we get the angle between these two, which is theta. And if the angle between these two is smaller than 90, this is positive. This is if it is greater than 90, then it is negative. We are saying that since this dot product is positive, it's non-negative, the angle between the vectors sigma minus sigma star and d epsilon p with their starting point coincidence. Putting this starting point there, we get something like that. The angle must be acute, okay, or less than 90 degree. If this is so, then this is correct. If it is not so, then it is not correct, okay. Supposing we have something like that, okay, that is the strain. If that is the strain, then for instance this vector, if we bring it over here, then the angle between these two is not acute, it's greater than 90 degree, and therefore this won't hold, okay. So in this way it is proven here that d epsilon p must be perpendicular to the surface f, okay, and we call that the normality condition. We can show this normality condition with this equation. What is this equation? D epsilon ijp is equal to d lambda partial f to partial sigma ij. Okay, here we have shown with tensor notation. It's the same as this vector notation, doesn't make any difference. This d lambda is a instantaneous constant, and because we have here an incremental strain, it means that it changes instantaneously. So this lambda also changes instantaneously, but it's constant. So that's partial f to partial sigma ij. What is this? What is it? This f is the yield surface. So partial f to partial sigma ij is perpendicular vector to the yield surface. So we call this the flow rule. Flow rule. Why we call it flow rule? Obviously flow of the material, because plastic deformation is the flow of the material. So it means that which direction the material flows, and is perpendicular to the yield surface. And plastic flow rule it's called, or plastic potential theory. We could substitute here partial u, partial sigma ij. It's the same thing as this. So if we put epsilon ij equal to partial u, partial sigma ij, this epsilon ij of course includes the elastic part, but the elastic part is very negligible. So this epsilon ij is equal to epsilon p. So this is in fact elastic strain. Okay, so we call this plastic flow rule or plastic potential theory. And note that here this is dependent on f. So we call it associated flow rule. Okay, associated because it is associated with the surface, yield surface. Okay, so here we have proven that d epsilon p must be perpendicular to the yield surface. That's one condition. Now the other condition is that in here, the other condition is that in here, supposing that the surface is not convex and it is concave, okay, we are supposing that it's concave, and if we draw a tangent to the surface, let me go back here. If I draw a tangent there, that's the tangent, and it's perpendicular to the tangent. Okay, so now I have a concave surface and a convex surface. So supposing on this concave surface we have a d epsilon p, and then if I draw a tangent to this concave surface, and supposing that the stress state, elastic stress is here, and the plastic stress is here. If we continue, put the starting point here and go in that way, and that is we have just translated it over here, and we got this angle which is more than 90. Okay, this angle is more than 90, so this becomes negative and it's not stable, so it's not correct. So we can't have a concave surface. And note that for this concave surface, when we draw the tangent here, we have some parts of the yield surface over the top in here and some part over the top here. While if the yield surface is convex, we have all the elastic regions on one side of the tangent and the plastic region on the other side of the tangent. Okay, so the entire elastic region lies on one side of the tangent plane to the yield surface if the yield surface is convex, which is the correct one. But if it is concave, as we can see according to the Drucker postulate, this becomes negative and unstable, which is not true for strain hardening materials, which are most materials are strain hardening. Of course, for strain softening also we have the same reasoning as well. Now you may say that, for instance, for Tresca yield criteria, we have sharp corners. So in this, and the epsilon p, we say that is perpendicular to the yield surface, which is this. Okay, so here the epsilon p is perpendicular, and here the epsilon p is perpendicular. So what happens at the sharp corner for the Tresca? Because at the sharp corner we have this one and we have that one, two, the epsilon p, both of them perpendicular. So at here what happens? As shown here, it can be shown that the plastic strain increment vector must lie within the cone bounded by the normal on either side of the corner, as illustrated here. So we say for the sharp corners, any of these vectors could be correct. Okay, so we have no problem on the sharp corners. Now in here, I have so far shown to you that the yield surface is convex and the plastic strain is perpendicular to the yield surface. Okay, so if we go back to the Mises criteria, which is this circle in the pipeline, then if we have a sigma ij a stress tensor, then we will have the plastic strain perpendicular to this, and so partial f to partial sigma ij is perpendicular to this surface as shown in here. Now this was the equation we derived before, but here we have added a dot on the top of the epsilon. We had the equation we had before was d epsilon ijp equal to d lambda partial f to partial sigma ij. Instead of d lambda and d epsilon, I have put epsilon dot and lambda dot. What does it mean? Epsilon dot, let's have a look what it means. It means this: d epsilon ij p over dt, d lambda over dt, partial f partial sigma ij. Now, what is this? This is in fact the flow rule. Associated flow rule is this one, not the one I showed you before, because flow, what is flow? Flow is the material moving with a certain velocity. So we have the rate, we should have the rate, and the rate is this, epsilon dot P. So that is the flow, okay? Because the material moves with a certain velocity shown with this. Epsilon dot means deformation per second. So lambda dot also brings in the time inside this term. So we have partial f over partial sigma ij times lambda dot. So we have the time factor in here and in there as well. We can write this like that. The epsilon ij p over dt, d lambda over dt, partial f over partial sigma ij, and then this dt with this dt is cancels out, and we get the same thing that we had before. So this has come from this part, okay? The flow rule is this, and we have shown it in this way and cancelled out dt, and we get this equation which we showed you before. Now, for the Mises criteria, we have f equal to j2 minus y2 over 3 equal to 0. That is because it's a circle, we have shown this before. Okay, we have shown this before. And so if this is the equation of the yield surface, then in here we can show partial f to partial sigma ij, okay? Because the epsilon ijp is equal to d lambda partial f over partial sigma ij, and this is partial f, that's f. So we write here partial j2 minus y2 over 3 over partial sigma ij. So the partial derivative of this is d lambda partial j2 over partial sigma ij, because this y is constant. What is y? In uniaxial tensile test, the yield stress is equal to y. So when we differentiate this sentence with respect to sigma ij, we get partial j2, and that one is 0, so just partial j2 over partial sigma ij, and we can write, and we know what j2 is, so this is known. This d epsilon ijp is known according to this j2 criteria. j2 criteria is Mises criteria. Okay, so for any other yield criteria, you can put f in here, and you will get the flow rule for that yield criteria. Another principle that could be noticed in here with the knowledge that so far we have gathered is the principle of maximum plastic dissipation. What does it mean, principle of maximum plastic dissipation? The epsilon ijp dot the sigma ij, in fact, is the work or energy done in order to get a deformation, plastic deformation, and the epsilon times the sigma, in fact, is the work done, and we say that it is dissipated. Okay, why we say it's dissipated? Because more than 95% of the energy or work is dissipated as heat, and the rest of it is dissipated inside the lattice in order to make the distortion in the lattice. So that's why we say plastic dissipation, and it is noted by this epsilon p. Right, now this was the Drucker postulate. Drucker postulate for stability. The quantity sigma ij epsilon dot ij is called the plastic dissipation, because as I said, this is the work or energy dissipated, and is a measure of the rate at which energy is being dissipated as the formation proceeds. Of course, because we have a dot here, the time factor comes in, so this is the power. This is the rate at which the energy is dissipated, and that is power. So that's the power dissipated. And as you can see from this inequality, if you put here sigma ij epsilon ij p, it means that this must be greater than sigma ij star epsilon ij p. So that is the principle of maximum plastic dissipation, which says, this inequality says, in vector form, in this form, we could write this as sigma, that's the vector, dot epsilon dot p, that's the vector again, sigma star epsilon dot is vector. This is the same as this, the same as this. The inequality is known as the principle of maximum plastic dissipation. It means of all possible stress states, we could have many possible stress states inside this yield surface, all kind of elastic. Okay, sigma ij star within or on the yield surface, inside the yield surface or on the yield surface, like sigma. The one which arises is that which requires the maximum plastic work. Okay, according to this, it means that this sigma, which is on the yield surface, is times dot epsilon dot p is greater than any work done inside this surface. Okay, so this is called maximum plastic dissipation. In fact, plastic dissipation, it means that the plastic work is greater than any work done inside this area. Okay, that is the idea. In order to further illustrate this, the principle of maximum plastic dissipation, which was this was of course the stability condition. From this we concluded that in order for the plastic deformation to occur, the maximum work has to be done. That's what we showed in the previous slide. In order to further illustrate this principle, I just like to apply it to a physical phenomenon, and this is a block on a surface, and we are applying pressure on it. So and we have friction on the surface, and we want to know how it moves. Application of the principle of maximum work dissipation to some physical phenomenon like the friction and the block. Now, here we are moving the block along this direction, so we want to move the block from A to B, and there is a pressure on the block, and we are just assuming that the friction is mu p in this direction, which makes theta with that direction. Of course, we know that this mu p must be in this direction, but for the sake of argument, we assume that it's in this direction, and that's theta. So, what is the work done? The block is moved from A to B, so the work done is this coefficient of friction times pressure, which is the frictional force. In order to move from here to there, we must overcome this frictional force. So that frictional force times that distance gives us the work done, moving from A to B. Now these are obviously the vectors, mu p and ds are the vectors, and and this is the scalar product, so we just put the magnitude mu p times ds times cos theta, because that's the product, dot product, that's cos theta. Okay, so it could be seen that for the maximum work to happen, theta has to be 0, and mu p goes along this line. So W is mu p ds. It means that force P acts in a way to maximize the work. This is called the principle of maximum work dissipation. Okay, so in the plastic dissipation, work dissipation also is like that, as shown. The plastic work dissipation also is like that, as shown here. You can see that we have this continuation of this line, and this is theta, the angle between these two lines. So here we have sigma ij, we have sigma minus sigma star times d epsilon p times cos theta, the magnitude of this times the magnitude of the epsilon p, times cos theta is always greater than 0 because cos theta is always between 0 and 1 because the epsilon p is perpendicular to the surface. So if this is so, then we get this relationship, which means that in order for the plastic deformation to occur, maximum work has to be done, and that's what we have shown here. To illustrate this idea further, note that this theta here, as in this expression, mu p ds cos theta, can change, can have different values, right? So supposing it have a 30-degree value, then this w will be less than it would be as theta is 0. When theta is 0, cos theta is maximum, is 1, and w is maximum. But any value other than 0 is not maximum, and it will be the value of w will be less than the maximum value. So when cos theta gets the maximum value, mu p comes along this direction, which is the right image, yeah, with where it should be, because this doesn't mean anything really. When mu p is along BA, that is the correct physical phenomena. Only we have shown here that theta can only assume the value of 0, and cos theta can only assume the value of 1 for this phenomena to happen. Okay, so that's what we mean, the principle of maximum plastic dissipation. We say the maximum work must be dissipated in order this happens, otherwise it won't happen. If it is here or anywhere else, it doesn't mean anything. The only way it happens is in this direction. Mu p is in this direction, and in that direction theta is 0. So that's what we mean by the maximum plastic dissipation, plastic work dissipation. And this physical problem is only to illustrate the concept. Now, so far we have talked about associated flow rule. Associated flow rule means that the epsilon p is perpendicular to this yield surface. But we have non-associated flow rules for many materials which fit to this rule, and it's shown by this. The epsilon ijp is equal to d lambda partial g to partial sigma ij. Note that this g is different from f. F is the yield surface, and g is another function which is not related to the yield surface. So that's why we say non-associated, because it's not associated with the yield surface. And in this case, the epsilon p could be inclined at other angles than 90 degrees. So it doesn't have to be normal to the surface, because we don't have the surface here. We have another function. So for many materials, hardening and softening, a non-associated flow rule is required, as in the above equation, like that. Here, the plastic strain increment is no longer normal to the yield surface, and the principle of maximum plastic dissipation does not hold in general. In this case, when there is hardening, the stress increment is directed out from the yield surface it is easy to see that one can have this, okay? Because you can have some like that, sigma like that, and d sigma like that, and d epsilon p like that. So the angle is greater than 90, and that becomes negative, okay? Contrary to what we have said for associated flow rule. For non-associated flow rule, this could be true. Above condition, this one, d sigma ij epsilon ijp is less than 0, contradicts the stability postulate. Obviously, the Drucker stability postulate says that this must be greater than 0. With hardening, with softening, this could be negative, but with hardening, this must be positive. But here it says it's not positive. So there is no obvious instability. But clearly here, because we have hardening, we don't have any instability. So how come this is negative? And so it could be argued that the use of term stability in Drucker's postulate is inappropriate. It says here that due to this non-associated flow rule, the Drucker postulate is not appropriate for the non-associated flow rule. It's only appropriate for the associated flow rule. And I tell you that in engineering plasticity, mostly we are dealing with associated flow rule. Especially in this class, we do not talk about non-associated flow rule anymore, but I just mentioned it because some materials in civil engineering, others like powder metallurgy, they may have to use non-associated flow rule. Again, here I have shown you the difference between these two. Obviously, this is perpendicular and this is not perpendicular because this is nothing to do with F. This is another function, potential function. Okay? So plasticity increment vector not normal to the yield surface gives you the non-associated flow rule like that.